terms of integrals. Okay, so hopefully this all looks familiar, right? When the velocity is greater than 0, it's moving right. Less than 0, moving to the left. What happens when it's equal to 0? Stopped, it's at rest. Okay, so displacement. So before, when we did displacement, remember when we would have our position function? We either used S or X. So think about displacement in terms of the integral. Right, think about when we take the integral, of velocity. What if we work backwards? If we take the integral of velocity, what would we get?
dx dt dt.
So, we would get S of t evaluated from A to B, which is S of B minus S of A. Isn't that how we represented displacement way back in like chapter 3? Okay, so understand that using integrals we can get to that same result. Okay, final position, that's our initial position plus displacement. So I can represent this. So let's say we know, or we want to find a position at some B. If I take my initial plus the integral, sorry, I'm running out of room here, from A to B of V of t dt. Ran out of room. All right, so I can find any position. We kind of had one of those on, I want to say it was one of the worksheets. Was it the practice test? I gave you like a value, f of 2 equals 9. This is where this comes from, right? It comes from a manipulation of the integral, right? And then total distance traveled. How do we find total distance traveled? Well, we want to take the absolute value of v of t, right? And we're going to integrate that, and that will give us total distance. What that does is anytime it goes below the x-axis, we want to count that as a positive. Okay, good. Okay, so we have a function, v of t is the velocity of the particle moving along the x-axis. So when is the particle moving right, left, and stopped? Okay, so when we did this in the past, I gave you position function. So we would have to do the derivative to find the velocity, but I already gave you velocity. So it's actually easier. What do we want to do? Set it equal to 0. All right. When is it moving to the left, to the right? We're just going to set velocity equal to 0. I gave you a real easy one here to start. What do we get for t? 8. Okay, so we're going to make a number line. It's going from 0 to 10, and then we'll put 8, and I'm going to label that as v. Okay, well, what happens from 0 to 8? If we remember, this is where we're going to plug in values. So if I plug, it's going to be positive, and then if I plug in something between 8 and 10, say 9, negative. So where is it moving right? From 0 to 8. It's moving left from 8 to 10 and stopped at t equals 8. Up. Okay. There. Up. There we go. It's on a delay. Any questions on that? Okay. So it's everything that we did before. We just didn't have to do the derivative. Okay. Now for B. We want to find the particle's displacement over the given time interval, so from 0 to 10, and we know S of 0 equals 3. So what are we trying to find? So we want to find well, let's look at displacement first. So the displacement equals, what was it? It was the, right, so we want to go from 0 to 10 of 24 minus 3t dt. Good? Okay, so what do we get? 24t minus 3t squared over 2, evaluated from 0 to 10. We might want to have a calculator handy. I forgot to mention that. So, yeah, what do we get? 240 minus, what, 300 over 2, so 150. And we get? You said 90. Okay. You did? Somebody said 90. Okay. It is 90. I was like, wait, I'm not tricking you again. Okay. All right, good. And just to check, we don't have, did we have any units? Yeah. Yes. So meters per second. So displacement, if it ends up being 90, that just means 90 meters to the right of where it started. Okay, so it's not that important to include units with displacement, but it is with like your velocity, acceleration, and so on. Okay, so what is the final position? So in other words, s of 10. So that's going to be s of 0 plus the integral from 0 to 10. But we already figured out this portion, right? You don't always have to show this much work. I'm just writing it out in notation so you kind of get used to it. Does that make sense according to what I had above? So what's s of 0? 3 plus our displacement, which was 90, which gives us 93. Oh, right, in the directions. Yeah. Okay, final thing. Total distance traveled. Okay, so now what do we want to do? The integral of the absolute value from 0 to 10. Good. Okay. Now, remember, if we have to do this by hand, which sometimes I'll have you do it by hand, sometimes you can just do it in your calculator. What's going to happen is we have to split this up into two separate integrals, right? So from 0 to 8, it's already positive, but from 8 to 10, it was negative. So I need to make sure I split it up. So from 0 to 8, and then how do I want to write the other part? You could subtract it, or you could just put from, oops, that's supposed to be an 8 to 10. And then just make sure to take the absolute value of that result because we want that to count as a positive distance traveled. Good? Or on your calculators, how would we do that just on the calculator? Which we'll do to save some time. Right, so we want to do, so we'll do 0, oops, 10. Where do we get the absolute value? Same place as the short. Yeah. Oh, it's frozen? I'm typing stuff. It'll show up hopefully. And if it doesn't, I'll plug into HDMI. Okay, so there it is. Right, so we want to do 24 minus 3, we'll use x. Oh, there is no squared. $102, save a little time.
You have to split it up into two integrals as like it
Oh.
passes through at 8.
Yes. So, okay, let's say the particle, if the velocity was positive the whole time, I wouldn't have to do that, right? But because from 8 to 10 is negative, I know my integral would end up being negative here. And so we would just want to make it positive when we evaluate that. I'm just trying to save some time by doing it on the calculator for now, because I believe we would be fine with that, right? Just be a little computation. Okay, let's try another one. Same thing, just different function. Oh yeah, 102 was the final answer.
Oh, 102?
102, does that not look like a 0? Sorry. 102 meters. And we definitely want to include units there, because that was how far it traveled. Okay, so what did we do on the last one? Where is it moving left, right, and stopped? What do we want to do? Set the velocity equal to 0. Okay, and note what our domain is from 0 to pi over 2. Well, the 6 as a coefficient, does that affect our zeros? No. So I want to find out what. Where is sine equal to 0? Okay, let's think about this.
0
At 0. Where else? At pi. I could do 2 pi, but again, I'm thinking I have to divide everything by 3. So, and I have to make sure all my values stay between 0 and pi over 2. So is 2 pi over 3 between 0 and pi over 2? No, so I don't really have to go any further. Question? No, oh, that's an equal sign. It was just a, sorry for my sloppy writing. Okay. Make a number line and, right, so it's got a starting at 0 and then somewhere. Okay. Okay, so just like before, right, we want to plug in. What should we plug in here? And also you can actually think about the actual function. Where is it going to be positive? Where is it going to be negative? So yeah, so if I plug in, let's say pi over 4, 3 times pi over 4, so 3 pi over 4 is sine positive or negative there? Positive. Question? I plugged in pi over 4. Listen, you know what a sine curve looks like, right? It doesn't matter, it's positive, so I know it's going to go like that. So what's going to happen between pi over 3 and pi over 2? It's going to be negative. So you can also just use like your knowledge of what sine looks like to know that's where, right? Because we know it's got to be equal to 0, those points, so it's got to cross the x-axis then, right? Okay, so it's going right from 0 to pi over 3. I am not including the endpoint this time because it's technically stopped at 0. Remember on the previous one I included the endpoints. Here, when is it moving left? From pi over 3 to pi over 2. Do I include the pi over 2? Yes. And then it stopped at 2 points. T equals 0. Okay. Because it's technically stopped at 0. So if it wasn't stopped here, I would include the endpoint. That's all. Okay. All right, let's save some time here. Let's do the displacement with the calculator. If you want to do it by hand, we can. You'd have to do a U substitution, right? So let's see here. So displacement. What are the limits of integration? 0 to pi over 2. And we want 6 sine 3t. If you have your calculator handy, want to make sure we have it in radians. Okay, so yeah, if it's in degrees from physics, just change it over to radians. You're going to be able to use your calculator a lot this chapter, so just a heads up, to have it handy. Okay, so 0 pi over 2, 6 sine of 3x 2. All that work to get 2. Okay. And what's going to be the total distance? Or sorry, final position. So we want s of pi over 2 is going to be what? We can jump right to it now. S of 0 was 3, so 3 plus 2. Yeah? Yeah. The right here, the initial. Oh. What's wrong? That's V. Because we're asking for the final position. So if we're looking at that endpoint, right, I'm trying to find the position at pi over 2. So I want to take the initial position plus the displacement. Listen, we've kind of done this before. It's just we're working backwards, right? When we did this before, I gave you the position function, and then you had to work with derivatives. Now I'm giving you the velocity, and we're working backwards. So we did the integral to figure out displacement, but then you just have to add your initial position to that. Okay? And then how about total distance traveled? So that's going to be what? 0 to pi over 2, absolute value of 6 sine 3t. Okay, if you were going to break it up, you would have from 0 to pi over 3, and then you would do from pi over 3 to pi over 2. That would end up giving you a negative value, so you would just want to make it positive, and you would add those two results together. What I'm telling you for the most part is to use your calculator for this lesson to kind of, a lot of what chapter 8 is show me the setup, and then you can use your calculator to evaluate. There will be places where you need to evaluate by hand, but a lot of it's going to be in the setup. Yes?
So we don't really need to break anything up. We can just leave it all together.
If I have it on the no calculator part, then you would have to split it up. If it's on the calculator part, I'll let you just show the absolute value, and then you could do it by hand. We're doing it on the calculator because of time. So I want to make sure we get to everything that we need to. Okay, so the nice thing is, you guys know that you can go back. Maybe you don't want to type this whole thing back in. You can select it and then put absolute value. Yeah? Or you can just type it all in over again. No? Are you guys still asleep? We didn't even have 0 period. Okay. Did you guys get an answer? What'd you get? Are you waiting for me to just type it all in? Just waiting for me. That's so nice.
I don't know about the right answer.
You don't think you got the right answer?
I got 0.38736002590. How?
Are you still in degree? Degree should I got 6.
I got 6 too. I'm pretty sure it's 6. Okay. All right. Okay, let's take a look. So, again, this whole chapter, most of it, like, remember when we did derivatives and then we did applications of derivatives? This is the application of integrals. Okay, so we have a car moving initial velocity of 5 miles per hour. That means v of 0 equals 5. It accelerates at the rate of 2.4 t miles per hour per second, note the units, for 8 seconds. Okay? So we want to know how fast is the car going when the 8 seconds are up. Okay. There's 2 ways we could do this. We could just, what? What are we trying to find? We're trying to find what's this asking for? We're trying to find v of 8. Now, I could find the velocity function, figure out what my plus c is, but my plus c is, what do you think my plus c is going to end up being?
8.
5. Or you can just integrate it. Because I'm also asking here, how far did the car travel? Then what? And is it going to be negative at all? Is there any negative velocity? So that kind of makes it a little bit easier. But let's look at part A again. How would I find v of 8? I can do v of 0 plus the integral from 0 to 8 of a of t dt. So just like when I was working with final position, this is final velocity. Does that make sense? So this one, when I'm trying to find a velocity, I want the initial velocity plus the integral of the acceleration. Does that make sense? It's the same idea, just instead of position, it's working with the velocity, but also working backwards from acceleration. Good? Okay. So what is that going to be? That's going to be 5 plus, here we can do this, 2.4 t squared over 2. So 1 point, what? Are you okay? Oh, I thought you said something.
1.6.
Now we want to evaluate this from 0 to 8. Maybe we'll use our calculator. What do we get? 81.8. Do I have to change anything with my units here? Okay, so this was miles per hour per second over 8 seconds. So because I integrated here with respect to seconds, I'm okay. I end up with just miles per hour here.
How did you get the 1.15?
Oh, sorry, I just did this without showing the work. This would be 2.4 t squared over 2.
Oh,
Sorry, I just,
got it.
okay. Now what? How far? So this is total distance traveled. How do I get total distance traveled? What do I need? The integral of what? The velocity. So, and again, this is going to be from, now this is going to be a little tricky because it's 0 to 8 seconds, but we're integrating with respect to a velocity function that's measured in miles per hour. Just keep that in mind that we're going to have to change the units. We can either change, oh, it's frozen again. We can either change these to represent hour, right? Or we can change it at the end. At the end.
how far it went?
Um,
Is it because I didn't have the
Yeah, right here. Remember, total distance traveled. It's going to be the integral of the absolute value of velocity. I didn't bother putting in an absolute value because the card's just going in a positive direction. Okay, what's our velocity function now? So keep in mind, what was our A of t? Yeah, remember, so we said v of t would be the integral of 2.4 t dt, which we said was 1.2 t squared, and then we'd have a plus c. But what happens when I solve for c? We already mentioned this, but maybe writing it out would help. If I plug in 5, plug in 0 for t, so my v of t is going to be 1.2 t squared plus 5. So this is what I was mentioning. There was 2 different ways we could find this. So I didn't have to necessarily set it up this way. I could have just found the velocity function and then plugged in 8. But notice, it's mathematically speaking, it's the same amount of work, essentially. Okay, so let's do 1.2 t squared plus 5 dt. Let's plug it into the calculator just to save time. And sorry, I didn't print out my answers, so I'll trust you guys, or I'll type it in. What do we get? Anybody? You got a couple people plug it? No? Okay. Yeah. 244 point. You got something different?
Oh, wait, no.
244.8. Is that exact? Or was there 3 decimals? Oh, great. Okay. Okay, so what do we need to do to this to get it in the right units?
Divide by 6.
Yeah, this was seconds. How many seconds are in an hour?
Oh,
3,600. So we're going to take, no, because we were measuring, this was in seconds. So remember, these are seconds, but this was miles per hour. So when I integrate it and the units don't match up, you could have changed this to 8 over 3,600 and then integrate it. It would get you the same answer. Or just take this and divide by 3,600. What do we get? Say that one more time. 0.068. And what are the units here? Miles. What would I get if I wanted to change it to feet? Multiplied by 5,280. Well, we won't worry about it for now. They might ask for it in feet. Okay. Any questions on that one? Okay. I do. I usually, again, mainly because like 8 over 3,600 would just look. Okay. Here we go. I think this is, oh, we still have 2 more pages. 3 pages. Uh-oh. Okay. Speed. Let's skip this one for the moment. I'll come back to it if we have time. So let's skip to the next page. Okay, total consumption over time. Yeah, because what time is it? 11? 9. Okay, 9:11. Okay, I know. Okay, so just like we were looking at total distance traveled can be represented as an integral, so is total consumption over time. And so what we're going to basically do is integrate whatever the rate is over time, and you get the total consumption. Okay, so again, these are all going to be calculator problems, so it's just making sure you have the setup correct. So 1970 to 1980, the rate of potato consumption in a particular country is measured by this function, 2.2 plus 1.1 to the t. Yes, millions of bushels per year. An actual measure, okay, right? T is the number of years since the beginning of 1970. Okay, so here's our rate. We want to know how much was consumed from 1972, the beginning, to the end of 1973, which correlates with beginning of 1974, if that makes sense. Okay, since I'm think like the very end. So set up the integral, and then we're just going to use a calculator to evaluate. All right. Really, it's just a matter of, we know the rate. The rate is 2.2 plus 1.1 t, or sorry, to the t. We just need to figure out the limits of integration. So think 1970 would be when t equals 0. So what are our limits going to be? 2 to 4. Because that's why I wrote here. We want to, this is the beginning to the end. So really that's 2 years, right? So if we're starting at the beginning here. Okay. That's really just it. It's literally like figuring out what are those limits of integration and then plugging it into the calculator.
How do you get 4 for the?
So if you think beginning of 1972 to the end of 1973, that's really 2 years. So this correlates the end of 1973, like think December 31st, 1973, is the same as January 1st. No, because if beginning in 1970 is 0, what would 1972 be? The beginning. Isn't that 2 years later?
Oh, so you added it from like 0. Like
Yeah, if this is 0, 1972 would be t equals 2, and this would be t equals, this would be t equals 2 to t equals 4.
Oh, I see.
Okay, did we get an answer?
7.066.
Sounds good. 6. And what are our units? Millions of bushels.
Well, I know, but I feel like it's like an actual measurement. It's just like
Yeah.
How many potatoes are there?
I don't remember. It's an actual unit of measure. I don't know offhand what it actually is. It's like, it's like a sack of something. I don't know. It's like a barrel, but for potatoes. Okay. All right. Oh, this should be... Oh, this is the graph of velocity. Okay. Oh, this should, where it says y, you could call that v of t. And my screen's frozen again. Oh, there it is. So this is velocity over the x-axis. What do we want to, oh, and the particle starts at x equals 2 when t equals 0. This should be t, sorry. This should be t-axis and v of t. So what are we trying to find? We're trying to find v of 10. So we need to do v of 0 plus the integral from 0 to 10 of v of t dt. Right?
Yeah, do you mean melodic displaces?
Oh, thank you. I'm sorry. I was doing end position. We didn't ask for that, did we? Hi.
But
Oh, wait, I was right. Wait.
Wait, but so why wouldn't you use her?
Sorry, I was
Wouldn't
right.
you use initial position and final position instead of
Final
Um,
velocity. Like, isn't that looking for?
Sorry. Sorry, I put the wrong letter. It was position. So we want the position at 10. So we take the initial position plus. Okay, thank you. Thank you. We sorted it out. Thank you. Okay. Yeah, that's VFT.
exact same time?
Okay, what's the initial? It's 2.
Yeah, I feel like you're about to unmute. Yeah, honestly, it's not like good luck.
Okay, what do we need to do? We need to figure out this area and this area. Okay, here. I'll do the trapezoid. So the height is 2, so 2 over 2. Base 1 is 3 plus 6. So that'll be 9. And then this one is a triangle. The base is 4, and the height is 2, divided by 2. So that will give us 4. But because it's below the x-axis, we want to make it a negative. So we get what for 7? And it doesn't look like I gave units, so we'll just leave it. And total distance traveled. Well, we did all the work for it. So with total distance traveled, we don't care about where it started. It went 9 units plus 4 units. So 13 units? Yeah.
3 plus 4, not 3 plus. Yeah. So the no.
Where?
No, because we're starting from X. We're starting from X.
Yeah. Oh, sorry. That was my height. I was just showing the height. Question?
What do you mean? You mean like
When I was doing this, I made the dotted line to show the height. No, you're starting at 0. Okay. What do you mean? This is the velocity function, not the position function. That's why. That's the total distance traveled.
oh my god, I added 9 plus
Because we want to count both areas as positive.
Don't look at that one. I said 9 plus 4, 16.
Okay, last question. Trapezoidal rule. Let's see if we could just do the setup. Did we forget the trapezoidal rule already?
No, we got it. We
It's
got
1
it.
over T.
T over 2. Are all of them evenly?
Yeah.
Yeah, so it's going to be 10 over 2 plus 2 times 65 plus so on, right? We're not going to have time to finish, but I'll post the solutions to it all. So if you want to try that other one. Okay, and whatever you get here, so this was over minutes, the rate was gallons per minute, so once we plug that in, we'll just get gallons. Okay, and then I'll go back and do that other example, but you should be fine without that one. I mean, I'm